So this is the last learning sequence in this course, and here we are going to discuss non-parametric methods. Well, you remember every time we want to make some inference, we use different parametric approaches, different tests, and most of them, of course, are based on the certain distribution of statistics. And these tests also have some requirements on the data quality. Most of them requires that data came from normally distributed population, have no outliers and so on, but it's not always the case. Quite often your data will not follow these requirements. For example, the distribution will be skewed, or you will have some extreme values, some extreme outliers and so on. So what to do in this case? Well, in this case we need to use non-parametric methods, and actually almost every parametric test has a substitute, a non-parametric substitute. We are going to discuss today what to do instead of one sample t-test, instead of two sample t-test, instead of ANOVA, how to calculate correlation coefficient if your data is not normally distributed, and how to calculate different confidence intervals without actually using any analytical functions. So that's the plan. The one sample t-test has two substitutes. It's a sign test and Wilkinson sign rank test. The two sample t-test has a good substitute as a Wilkinson rank sum test, or sometimes it's called also Mann-Whitney test. For ANOVA, unfortunately, there is no substitution for n-way ANOVA. We can only do one-way ANOVA with one factor, and it's a Kruskal-Wallis test. For the correlation, we have to use Spearman rank correlation coefficient, and for confidence interval, we will use a procedure which is called bootstrapping. Okay, so let's start. First of all, the main idea of all the tests we are going to discuss today, it's ranks instead of values. You remember rank is just a position of the value in the sequence when you order the values from the smallest to the largest, and then you can define a position of every value, 1, 2, 3, 4, 5. So we are going to use ranks instead of values. So it means that you already know quite a few statistics that are non-parametric statistics, like median, percentiles, quartiles. They all based on ranks, and therefore they are non-parametrics. They do not require any distribution. So let's start with the first case, what to do if you have one sample and you would like to know something about the average value on the population. Okay. Well, you know that in parametric approach we use this one sample t-test, right, for average value. Unfortunately, average value is very sensitive to all kind of outliers and on non-symmetry in your distribution, so we cannot use average value here, but we can use another statistics which is also very good to estimate the center of the distribution, which is median, right? And median is quite stable to problems in your data. So it means that we are going to make a test for a median of population, and actually there are two possibilities, two different tests. It's a sign test and Wilkinson sign rank test. Well, in reality, you will always use the second, but I would like to start with the first because it's very intuitive. It gives you an idea how actually non-parametric methods work. So we are going to use the same example as we used for the t-test. It's chloride content in two rivers, Wada and Ribe, and because in this case it's one sample t-test, one sample test, I'm going to use Ribe as an example. And my null hypothesis will be that median chloride content in the whole river in Ribe is 146. Okay, I will not discuss the tails because I mean you know already how to calculate this for tails as well, but I'll show you how to do it in R at least for different tails. Well, the idea is extremely simple. Think. 146, it's median. What do we know about median values? We know that median value should split all our values 50-50, right? So it means that you have 50% of the values below median and 50% of the values above median. So the ideal sample will be where you have the same. So if you have, for example, 10 values, 5 should be below median, 5 should be above median. But sample is not the population, so you will always have by chance a little bit smaller values or a little bit larger values, right? So can we use this knowledge to make a test? Yeah, we can. We just need to find out how many values in our sample are below median, how many values in our sample are above median, and then use some distribution that describes the behavior of this. Okay. So that's the formal instruction. Take a difference between observation and tested value. So just take every value and subtract the median. Then assign a sign. So instead of the values, you need to use a sign. So if it's below median, it should be minus. If it's above median, it should be plus. and then count how many values are positive and how many values are negative. Take the smallest one and get a p-value. So it means that we need to know the distribution of these minuses and pluses. We will discuss it in a minute. Okay. So that's the data we have. That's our null hypothesis. Median is equal to 146. Now look, let's calculate how many values. Let's count how many values we have below and above, right? So the first value is 135. It's below, so it's minus. Then it's above, so it's plus. It's below, so it's minus. And then we just continue doing that. And then we will find out that we have only two pluses, and 8 minuses. Okay. So in reality, it should be 5, 5, but we got 2 and 8. How extreme the sample is. Okay. Well, first of all, we will use the smallest value, 2, and then let's think a little. This situation is very similar to coins, right? So every time we toss a coin, if probability to get tail is 0.5 and probability to get head is 0.5. Okay. So it means that every time we toss a coin, we expect to have equal amount of tails and heads. But sometimes number of tails is smaller than number of heads, or vice versa. It's still possible, right? We just need to calculate this probability. Okay. This case actually has a certain distribution, and it's called a binomial distribution. It was invented by Isaac Newton, the English mathematician and physicist. And he found out that in this case, if you have an event and you know the probability of this event, for example, in our case with coins, event is getting a tail, okay, and we know the probability to get a tail. Then if you make n trials, so if you toss a coin n times, the probability to get k successes can be calculated using this formula. This little in squares, it's called binomial coefficient. This is how to calculate it. And if you forgot or don't know what this exclamation mark means, it's called factorial. For example, n factorial is n times n minus 1 times n minus 2 and then up to 1. Okay. For example, if you have 3 factorial, it means 3 times 2 times 1, which is 6. Okay. And then 0 factorial is always 1. So you calculate these coefficients, and then you take the probability to get a success in power of k, and the probability to get a non-success in the power of n minus k, and then you multiply all three together. Okay, so it's relatively simple. Let me show you an example using this coin case. Okay, so we would like to toss a coin 10 times. The probability to get a tail is 0.5. What's the chance to get, for example, 0 tails? Or 1 tail, or 2 tail only. Okay. Well, we can calculate this chance. For example, if you want to get only 0 tails, to get a chance only for 0 tails, that's how the formula looks like, right? So the k is equal to 0 in this case, and then we just put all the numbers and calculate the probability. It's 0.1%. So it means that if you make it 1,000 times, then probably in one cases you will get 0 coins, 0 tails. Okay. Then we can calculate the same for 1 tail only. In this case, the probability is a bit larger, it's 1%. Then for 2 tails, for 3 tails, for 4 tails, for 5 tails. And for 5 tails, of course, the probability will be the largest because it's the least extreme sample, right? And then if you start calculating it for 6, 7, 8, it will be just the opposite, because in this case, probability is symmetric, because the probability for tail is 50%. Okay. Then you can make a function, this density mass function, which looks like a histogram, because in this case we have discrete values, not continuous values. Okay, so the height of every bar is actually the probability. Okay, so that's how it works. So that's our case. I just recall we expect to see 5 minuses and 5 pluses, because in this case n is equal to 10, but we got 2 pluses and 8 minuses. How likely we can get it if null hypothesis is true? Well, you remember the p-value is a chance to get a sample like we have, or even more extreme if null hypothesis is true, right? So this is the distribution for our null hypothesis. What's the chance what's the sample as extreme as ours? It's because it's 2 tails, it will be 2 and 8, right? So it's either 2 tails or 8 tails. What the samples are more extreme? Of course, it's this direction, right? So if we calculate the height of these bars and sum up, we will get the p-value for our null hypothesis. And the p-value is 0.10, almost 11% chance to get a sample with only 2 pluses, and 8 minuses if, in fact, for population it should be 50-50. Okay, so in this case we cannot reject our null hypothesis, of course. And then if you want to do it in R, you need to use a function that is called binomial test, and it requires 2 arguments. How many successes you have. It's the smallest of minuses and pluses, right? So in this case, you can see how I calculate it. I just compare my values from X with a predefined median value. I use mu0, it's not quite correct. It should be median, of course, but it doesn't matter in this case. So I compare how many are larger. I know that I have only 2 larger, right? So that's the smallest. And then I also calculate the size of the sample. You can just, instead of this, you can just write 10 if you know it. And then the binomial test gives a p-value, gives the probability. If you want to make the test for one tail only, for left or right tail, then you just provide additional argument like we did before. It's alternative equal to greater or alternative equal to less. So that's how it works.